Yeah, we're going to continue on here and talk about acids and bases and wrap it up, hopefully. So last time we talked about, again, weak acids really and weak base type problems. And remember that with a weak acid or weak base, they are weak electrolytes, which means they do set up an equilibrium. And that means that we will solve these sort of problems like normal. We will need to do an ice table. And depending on really sort of what you see on the product side as to really, should you be using a Ka value? Should you be using a Kb value? Again, if you see H plus or H3O plus on the product side, you should be using the Ka value, which is the weak acid dissociation. If you see hydroxide on the product side, that's definitely a base type problem. The difference is really between these two things is we pretty much need to do an additional sort of calculation at the end of these problems, because usually we're interested in either the pH in the case of a weak acid or the pOH in the case of a weak base is really what we could get. So when we do solve the ice table for a weak acid problem, when we do solve for X, that will be the H plus concentration, which means we can go into the pH equation at that point with it. But when we do the ice table there for a weak base, when we solve for X, it will be the hydroxide concentration, which means we really do need to go to the pOH first and then to the pH. So there's a couple extra steps that you typically got to do on that situation. We also talked about the relationship between Ka and Kb. If you take Ka value times Kb value, that equals Kw, which is very helpful for what we're going to talk about here in just a second. And that does equal 1 times 10 to the minus 14. So again, there are certain problems where you will be given the wrong sort of K value, if you will. You'll be given a Ka value when really in the calculation, you do need the Kb value. Thank you. And you may be given the Kb value in a calculation where you really do need the Ka value. That's why, as I mentioned several times, it's really important to be able to write these equations correctly, because they will help you sort of figure out, should you be using the Ka value or the Kb value when you do it. We also sort of finished up, I think, talking about acid strength. And really, the strength of an acid depends on what type of acid you're sort of looking at. If it's a acid with no oxygen, then we look at bond strength as the overwhelmingly sort of a characteristic that helps us determine it. The stronger the bond strength, the weaker the acid. So that is why something like HF is a weak acid, as it has a high bond strength between the hydrogen and fluorine bond, while something like HI is more of a strong acid, as the bond strength between the hydrogen and the iodide is less. What makes something an acid is the ability to release that H plus. So the lower the bond strength, then the easier the H plus will come off. We also talked about oxyacids, and those are obviously acids that contain oxygen. And when they do contain oxygen, there's really one or two things that we look at. We either look at the electronegativity of the central atom, or we look at the oxidation number of the central atom. And in terms of acid strength, it does increase with both. So the higher the electronegativity value, then the stronger acid would be, because really in that case, you usually will have this type of bond here that's polar to begin with. So more electronegative or more higher oxidation number will bring those electrons further in and further weaken this OH bond and really allow that hydrogen to come off and basically act as an acid. We look at oxidation number when we have basically the same element and it has basically the same electronegativity value. We look at electronegativity when we have different central atom that has the same oxidation number. So if the central atom has the same oxidation number, you would look at electronegativity. And if the central atom has basically the same electronegativity, you would look at oxidation number to help you decide which one's which. Any questions on any of that stuff there that we talked about? All right, then the next thing we're going to talk about are salts. And as hopefully you remember from chemistry, when you take an acid and a base, you basically form two things. You form water and a salt. And a salt is really just an ionic compound. And the salt part can be important in terms of the pH of the solution. And this is really important to think about sort of where the salt comes from and also understand sort of the relationship that we talked about earlier on. And that relationship is if it comes from either a strong acid or base, its partner is going to be relatively weak. So its conjugate partner will be weak. And vice versa, if it comes from a weak acid or a weak base, its conjugate partner will be relatively strong. And this is really where that relationship comes into play, is understanding that when we have sort of a strong conjugate base or acid that came from a weak acid or weak base, what we mean by it being strong is, frankly, it will continue to react. And who is it going to react with? Well, it's going to react with the water that is there. So what happens in certain cases is, as salts are sort of made as a result of a reaction of an acid and base, that salt will continue to react with water and will affect really the pH of the solution. So let's talk about some of the different types of salts that we could come across. Pretty much there are some neutral salts, and neutral salts are really any salts that contain an alkali metal or an alkaline earth metal. Those are group 1 and 2 on the periodic table. And as we talked about, that is pretty much where you find your strong bases come from. So a lot of strong bases come from group 1 and 2 on the periodic table, which means that if you have a metal that comes from group 1 or group 2, it's going to be relatively weak as a counter to that. So anything that really comes from a strong acid or strong base will be pretty much a neutral salt. And we would expect the solution to have a pH of 7, which is neutral. And what that really means is we would not expect that salt to continue to react with water. So if we had something like sodium chloride, which is a salt, and if we had to take a guess as to what acid and base made sodium chloride, what acid and base probably made sodium chloride here? Not everyone at once. That would be hydrochloric acid plus a little sodium hydroxide is probably the acid-base combination there. Switching partners. Sodium and the chlorine come together. Hydrogen and hydroxide come together to make water. So HCl is a strong acid, which means really the Cl minus part of that salt is going to be relatively weak and not continue on and react with water through a reaction that's known as hydrolysis. And the sodium ion, which actually comes from sodium hydroxide, will not continue to react either. Yes. It means in this case, you took solid sodium chloride and you dissolved it in water. And when it does, then that's when you get your aqueous ions, basically, yeah. So remember that, you have only really ions in solution. So that's really where ions are. Things with charges floating around are in a solution, yeah. Yeah, it's the same idea sometimes, yeah. Yeah. But sometimes for just solids, just to show the process of dissolving, put something like water up on the arrow to indicate that it was dissolved in water. Yeah. Other questions? Okay, so if you have really anything that you could derive comes from a strong acid or strong base, and really group 1 or 2 on the periodic table, you would expect it to be a neutral salt, no hydrolysis, no further reaction. You would expect that salt solution to be basically neutral. Now, if we take something like sodium acetate, which is this guy. When we have something like sodium acetate, it is an electrolyte. So when it's in solution, it would break apart into a sodium ion and a acetate ion. So this is our salt here. And if we had to take a guess as to what reaction or acid and base made these two things, acetate would most likely come from acetic acid. And the sodium most likely came from sodium hydroxide. Again, double displacement here. These guys are going to switch partners. Going to make some sodium acetate and some water in this case. Yeah. So when we have a salt like this, it really is a source of two ions that are floating around that solution. We have our sodium ion, which, as we talked about up here, is really from sodium hydroxide, which is a strong base. It's also from group 1. That means that really this guy is neutral. So it's really not going to go on and react with anything. But when we look at the acetate part of this salt, because it really did come from acetic acid, which is a weak acid, that means that this salt is going to be relatively strong. Again, not as strong as a strong base, but it will be strong. So it will have the potential to continue to react with water, which happens to be in the solution to begin with. So what's going to happen here is we will get a reaction between acetate and water. Now, the other sort of relationship that's important to remember is if we think about it sort of backwards here, obviously it came from a weak acid, which means this would technically be the conjugate base. Yeah, so that relationship. And the definition of a base is something that will accept an H+, which means now we know how it's going to react with water. It's going to actually accept the H+ over there, as it's going to act as a base when it reacts with water. The result of that is here we will make acetic acid, which, by the way, you always make where it came from, which in this case is acetic acid. And we will make a little hydroxide action here. Now, without doing any calculations, we should know that this solution should be basic because we have produced hydroxide. So again, here we do see hydroxide on our product side, which tells us it should be basic. And by the way, if I were to do an ice table, which you would need to do in this case, I should be using a K what? Ka value, Kb value. Kb value, that's a good answer. Yes, we should be using a Kb value because we do have hydroxide in the reaction. This is historically the type of problems where they will give you the wrong K value. You probably would have the Ka value in this case for acetic acid. This is a situation where you would need to use that Ka times Kb equals Kw to swap it around to the right value. We would, if we wanted to calculate the pH here, roll out with a ice table. We would solve for X. In this case, though, X is going to equal the hydroxide concentration. So when we solve for X, it will be the hydroxide concentration, which means we would have to do a little POH action and then to the pH action on this. So in this type of salt, which basically originates from a weak acid, we do expect the actual salt to continue on and react. And again, in this case, it will produce hydroxide, which means we expect it to be a basic solution. And we do expect that we need to use a Kb value to solve for it. Question on that there. Pretty much what that says. Now, there are some salts that are acidic. So for example, if we take something like ammonium chloride, which I think is what you got on your paper there. So we have some ammonium chloride. This would be the ammonium ion and the chloride ion here. Once again, if you want to think about it in terms of where it came from, what acid and base basically made this, hopefully you can figure it out, but just in case, it should be hydrochloric acid and our good friend ammonia. And in this case, we will make NH4Cl as the H will come over here. You also could break these apart exactly like you have it there, NH4 plus and Cl minus as well, if you don't want to keep them together. So in this case, we already know from our conversation earlier that the chloride comes from HCl, which is a strong acid, which means the chloride part of this salt is going to be basically neutral. So it's going to be relatively weak. It's going to be a neutral salt. Once again here, though, the NH4 plus part comes from the NH3. And the NH3 is a weak acid, which means that the NH4 plus will be a relatively strong conjugate base. Sorry, I did that backwards. Let's try it again. NH3 is a weak base. There we go. And this will be a conjugate acid in this case. Sorry about that. NH3 definitely a weak base. So NH3 is a weak base, which means NH4 plus will be a relatively strong conjugate acid. And what that means, again, in this case, we would expect it to continue to react with water that's in the solution to begin with. So what we're going to get in this case is a reaction between just the NH4 plus part of the salt. It will react with water. And once again, knowing that it is the conjugate acid, it is going to send it over the H plus. The result of that is, once again, as I mentioned before, it will always make where it came from. So it will make NH3. And in this case, when the water picks up the H plus, it will make H3O plus. Without doing any calculation, if you wrote this formula correctly or equation correctly, we should know that this should end up being acidic because we are producing H3O plus in this case. We also, again, if we were going to roll into an ice table to actually solve the pH of this solution, should be using a Ka value because there's H3O plus there. Once again, most likely in this problem, you would be given the Kb value for NH3. So again, it's a very common thing with salts that you sort of are given the wrong K value there. Once again, though, when we do the ice table here and we solve for X, X in this case will actually equal the H plus concentration, which means we can go right into the pH at this point and calculate it. So if you have a salt where part of the salt does come from a weak base, that part of the salt will behave as a relatively strong acid in the sense that it will go through the hydrolysis reaction, which is what this is referred to because it's reacting with water. And it will produce basically H3O plus, and you should expect an acidic solution to occur. Any questions on that there? Now, there is another way that we can sort of produce a acidic salt, and that is from actually some small, highly positively charged metals. A lot of transition metals, for example, aluminum is an example. And in this situation, what we have is, if you look at this thing, it looks kind of scary, but later on, you'll know how to name it properly. We will have an aluminum, and it basically means that there are 6 waters attached to it through the oxygen, really. 1, 2, 3, 4, 5, and I'll draw one out here. And what happens in this situation is all these waters are attached to the aluminum, which has a +3 charge. Again, that's going to kind of really weaken one of these bonds and bring the electrons in. And what ends up happening is another water, just by itself, not attached to any metal, will come by basically and steal off a hydrogen there from it, this complex ion, which is really what it is. And the result of that is it will form H3O plus in this case, which is the hydronium ion. And that's basically what that is. And if you're keeping track of the math here, we pretty much didn't do anything to 1, 2, 3, 4, 5 waters, which is why there's still 5 waters there. And the one water that we did something to, the only thing that's left is an OH, which is where the OH comes from here. And we lost an H plus, which means when you lose one positive, you become one less positive, and that's why the charge changed to +2 in this case, because we did use that H plus. So this is another common way that you could kind of produce an acidic sort of solution, kind of small transition metals. Again, a lot of times can do that with kind of +2, +3 type charges, have the ability to do this sort of reaction, actually produce H3O plus in solution. Any questions on salts here? All right, then let's do some here. What is the pH of a 0.45 potassium chloride solution? Take a minute or two and see what you see here. So this is KCl, which means that that is the salt, which will break apart into K plus and Cl minus. So really what we want to look at here is, will any part of that salt go through hydrolysis, will continue to react? Most likely this KCl came from the combination of what two things? What acid, what base here? Most likely it was HCl and KOH. Yeah, that's most likely what we got going on there. That would give us some water there and a little KCl there. So first off though, K plus obviously in this case came from KOH. It is also group 1 on the periodic table, which means the potassium ion is a neutral ion. Yeah. It is relatively weak because it comes from a strong base. The Cl minus, as we've been talking about, most likely came from HCl, which means HCl is a strong acid. So that would be relatively weak as well, and also neutral. So in this particular case, no calculation needed. The pH should be 7. It should be neutral in this case. Again, you basically have a neutral salt. Both parts will not continue to react with water in this case. Any questions on that there? All right, so let's take a look at one where you do need to do a calculation. So we'll do the next one here. All right, so this one you do need to do a calculation. Consider a solution that is 0.3 molar NaF. Ka value for HF is 7.2 times 10 to the minus 4. We're looking for the pH here, I think. Okay, let's take a look, see how you're doing. So we definitely have a salt here. So once again, you want to think about the salt breaking apart in solution as it's swimming around in there. We got some sodium ions floating around, got a little fluoride ions floating around. So now really the decision again here is, will any part of this continue to react with water and go through hydrolysis? Will any part of it go through hydrolysis? It will. So let's take a look here. The sodium, once again, is a group 1, which means it's neutral, so it will not go through hydrolysis. F minus, though, on the other hand, will go through hydrolysis. And again, you don't want to overlook some information that's given to you in problems. I see here I have the Ka value for HF. Ka would imply that HF is a weak acid, and that is most likely where that came from, which would imply that that's going to be the conjugate base and going to actually go through hydrolysis. So don't overlook the information in the problem. It makes it easier sometimes to focus. So we do know that F minus comes from HF, which is a weak acid, so it will go through hydrolysis. So we do want to scribble all over the paper, I think, in this case. We do want to write the reaction here. So we're going to take F minus is going to react with water. And once again, it is going to react as a base, which means it's going to accept the H plus. By the way, logic also tells us that there is no way it can donate an H plus because it doesn't have it, right? So it obviously has to accept it in this case. Again, if you're not sure how to finish the reaction, this also gives you pretty much a product. So that is what's going to go on the product side as well. So it will make HF. And when water loses the H plus, it will produce OH minus. So once again, by writing this correct equation here, I should know right off the bat that we will not, that this solution will be acidic, basic, or neutral. It should be basic because we are producing OH minus in this case. Yeah. Any questions on? All right. I think froze there. We are going to do our ice table here. So we have our initial concentration F minus, which is 0.3 molar. And remember that if this guy is 0.3 molar, it is a 1-to-1 relationship between the sodium ion, also a 1-to-1 relationship between that and the F minus. So the concentration would be 0.3 molar as well. This is going to be 0 and 0. Change will be minus X plus X plus X, which means at equilibrium 0.3 minus X, X, and X. Any questions on the table here? At this point, we're going to put it into our K expression, which is HF times OH minus divided by F minus. And this is a K what? A, B, C, D, F, G? This is a KB that we need to use because we do have hydroxide here. Once again, we are not given the KB value, but we're given the Ka value. So we do need to swap it out there by using Ka times Kb is equal to Kw. That means that the Kb value here would be 1 times 10 to the minus 14 divided by our Ka value, 7.2 times 10 to the minus 4. And that will give us 1.4 times 10 to the minus 11. So putting in our values there gives us x squared over 0.3 minus x equals 1.4 times 10 to the minus 11. That definitely is a small value of k, which means we can make our assumption and assume x is equal to 0. That will give us x squared over 0.3 equals 1.4 times 10 to the minus 11. We're going to multiply this to the other side. We're also going to take the square root of it. And if we do that, we will end up with an x value here of, we'll call it 2.04 times 10 to a lot of zeros. 1, 2, 3, 4, 5, 6, minus 6, I think. We do want to check it. So we're going to take this and divide it by 0.3 and times it by 100%. And in a lot of cases with the hydrolysis problems, you're usually in pretty good shape. We're not even 1%. We're way, way under it. So this is okay. The check is good. So this would be our X value. And once again, here our X value equals from our table the hydroxide concentration. So not the H plus concentration. So that means that the POH would be minus the log of 2.04 times 10 to the minus 6. So minus the log there. 2.04 to the minus 6. Gets you like a 5.62 POH. So once again, that is the POH and not the pH value. So we do still need to subtract 14 from it. That's good to know. It's good to know you can't do that. All right. So the pH here is 8.38, which does make sense as this is a basic solution and we would expect a basic pH here. Any questions on that there? So again, important parts of this, people struggle with writing the reaction, using the wrong K value, very common mistake, and mixing up because frankly, they cannot write the reaction. not knowing when they get the X value, is that the H plus or OH minus. So again, really important to be able to write those things so that you know when you do solve for X, what it actually is. All right, let's try another one here. Hopefully we won't have so much technical difficulties here. Give this one a go. All right, give this one a go. What's the pH of a 0.75 sodium cyanide? Sodium cyanide. And again, when that breaks apart, it does break apart into a sodium ion and a cyanide. We've talked about up to this point that obviously sodium is a neutral salt, so we're not going to worry about it. CN minus, again, in case you're not sure, we do see a Ka value for HCN, which tells us that that obviously is a weak acid and pretty much where that came from. So we do know that it will go through hydrolysis because that is a weak acid, so it's going to be relatively strong. We also know because that is a weak acid, this once again will act as a base when it's reacted with water. So that is where we want to start with our CN minus plus our water. Once again, going to accept the H plus in this case. And as I mentioned before, will pretty much always form where it came from, which would be HCN. And that will give us some OH minus. So once again, just like the previous one, we are forming hydroxide here. So even before we do the calculation, we know that this solution should be basic. So again, it's a good way to check yourself at the end just to make sure you didn't mess up. You should definitely end up with a basic pH. We will do our ice table here, which would be 0.75, 0, and 0. Change will be minus X plus X plus X. And at equilibrium here, 0.75 minus X, X, and X. Any questions on the equation or the ice table? Once again here, that's going to go into our K value, which is in this case HCN times OH minus divided by CN minus. And also because of the OH minus, this should be, again, a KB value. So very important to keep that in mind. We will do our little kind of flip around here to get to the KB, which would be KW divided by the Ka value. And once again, KW is a constant, 1 times 10 to the minus 14, divided by 6.2 times 10 to the minus 10 in this case. This gets us 1 to the minus 14 divided by 6.2 to the minus 10. And that will give us a KB value of, we'll call it 1.6 times 10 to the minus 5, I'm assuming. 1, 2, 3, 4, 5. There we go. So putting in our values here gets us X squared divided by 0.75 minus X equals 1.6 times 10 to the minus 5. Once again, we're going to assume X is equal to 0 here, and that would get us X squared divided by 0.75 equals 1.6 times 10 to the minus 5. We're going to multiply it to the other side, the 0.75. We're also going to take the square root of it after we do that. And if you do that there, you will end up with an X value. I'll put it up here. We'll end up with an X value of, we'll call it 3.48 times 10 to the minus 3. We do want to check it, so we will divide this by 0.75 and times it by 100% and make sure it's all good, which I'm assuming it is. It's about 0.4%, so the check here is good. Once again, when we go to our ice table, our X value is, again, our hydroxide concentration in this case. That means that our POH we could get from that. And that would be minus the log of 3.48 times 10 to the minus 3, minus the log 3.48 to the minus 3. Gets us a 2.46 POH, and then to our pH, which would be obviously 14 minus 2.46. And if we take that there, we're going to end up at 1154, which is a basic pH. and does make sense here. Any questions on any part of that there? Now, in this particular case, these couple examples, we produced hydroxide. You obviously could have a salt like we talked about that could produce H+. The only difference is at that point, you could go right into the pH equation. Once you calculate the ice table, you would need obviously the Ka value in that case. Any question on salts? All right, so let's finish up the rest of this here, I think. All right. Now, in the examples that we did and we talked about, only one part of the salt actually went through hydrolysis. It is possible that you could have a salt that actually both parts go through hydrolysis. For example, if you had a little NH4NO2, yeah, that's ammonium nitrite. Yeah, that probably came from ammonia. And this one came from nitrous acid, not nitric acid, which is a weak acid. In this case, actually, both of these guys have the potential to go through hydrolysis, NH4 plus and the NO2 minus. So in a situation like that, when you have a salt where actually both parts could go through hydrolysis, to make the calculation easier, we don't do both salts. We actually compare the Ka value to the Kb value. And if you compare the Kb value to the Ka value for the cation and it's larger, then the solution will be basic. You basically do the Kb calculation. If you compare the Kb value and it's less than the Ka value, then it will be acidic. And you basically would do just the Ka part of the calculation. And if they're about the same, it's going to probably be a neutral sort of salt. So when you do have both parts of the salt that can go through hydrolysis, you compare the Ka to Kb value, and really whichever one is larger, you just go through that calculation, either calculate the H plus concentration or the OH minus concentration using the Ka or Kb, whichever one is actually larger. Any questions on that there? I would say probably a majority of the time, the ones that you would be given would probably be just one part of the salt goes through it. But again, it is potential that both parts can go through hydrolysis. All right, let's talk a little bit about oxides. Oxides are metals and nonmetals that contain oxygen. And there are certain oxides that are basic oxides. There are certain ones that are acidic oxides. In group 1 and 2 here, where we have a lot of our strong bases come from, these oxides, when they react with water, will produce some of the strong bases like sodium hydroxide, potassium hydroxide, and so forth. On our nonmetal side over here, this is where we will produce basically acids. So they're acidic hydroxides. That's where things like, for example, a little bit of water and some CO2 will make some H2CO3, which is carbonic acid. So you can make some carbonic acid from that carbon and oxygen together. Things like nitric acid is made in that region as well. There are some that are amphoteric, which are these guys in kind of orangey color. And as we talked about, amphoteric means that it can act as either an acid or a base. So it can kind of go both ways when it reacts with water. So kind of the left side of the periodic table are basic oxides, right-hand side upper where the nonmetals are acidic oxides. Now we talked about a couple of definitions of acids and bases, and we're going to talk about another definition. We talked to the Arrhenius acid, which produces H plus in solution. Bronsted-Lowry acid is a proton donor. So our good friend Lewis wanted to be involved. So there are Lewis acids and Lewis bases. And when we think about Lewis, we think about Lewis structures. And when we draw Lewis structures, what's involved with those? Those are electrons. Yeah. So his definition of an acid and base is actually involves electrons. A Lewis acid is a electron pair acceptor. A Lewis base is an electron pair donator. So a Lewis base will donate a pair of electrons, a Lewis acid will accept it, and that's because a lot of Lewis acids are positively charged. They're electron deficient, so they're able to accept those electrons. A lot of Lewis bases are things with negative charges, which means they have extra electrons to give. Are there things with a lot of non-bonding electrons and are polar type of compounds? Things like water is a good Lewis base. Things like ammonia, also a good Lewis base. If you draw ammonia right, it's got some non-bonding electrons there on the nitrogen, and it is polar. So an example of that here, if we look at it, we got our hydroxide donating a pair of electrons, which means it's going to act as the Lewis base. This is going to act as the Lewis acid because it's going to accept those pair of electrons. It's positively charged, so again, it's electron deficient. Here again, our ammonia is going to be able to donate those pair of electrons because it's really polar, and it's going to be a base. And again, here our H plus is going to be our deficient in electrons and accepted to be the Lewis acid. It is really the same definition as, or you come up with the same result, I'll put it that way, as you do when you talk about a Bronsted-Lowry acid and base. This is the guy that's donating the H plus, so he's the acid. That's the one accepting the H plus, so it's the base. So it does come out the same in terms of which one's the acid or base, regardless of sort of what definition you go by. The benefit of a Lewis acid and base is something like this, where we have actually no hydrogens being transferred here. So in this case, our nitrogen here is going to donate the pair of electrons to boron. As you might remember, boron is an incomplete octet, which means it has less than 8 electrons. It is electron deficient, which means it will accept it, making this guy our Lewis acid, and this guy being our Lewis base in this case. And again, no actual H plus being donated or accepted, so you could apply Lewis acid and bases to sort of a non-proton sharing situation or donating situation. We will see Lewis acids and bases in a future chapter a lot when we talk about transition metals, complex ions, and stuff like that. So that definition is used a lot just to kind of demonstrate types of reactions that are occurring. Any questions on a Lewis acid or base? All right, the last we're going to talk about in this chapter are polyprotic acids. So some acids are monoprotic, like this guy here, can give away 1 H plus. Some are diprotic, which can give away 2 H pluses total. And some can be triprotic, which in this particular case could give away 3 H pluses here. Now, when we do have a diprotic or triprotic situation, the H pluses do come off basically one at a time. They all just don't drop off all at once. It is sort of a stepwise fashion as to what happens there. So for example, the first thing that happens with H2SO4 is that it will lose 1 hydrogen and make HSO4 minus. Then that guy will lose a hydrogen and make SO4 2 minus. Is it easier to take off the first hydrogen or the second one? Which one should be easier to do? Anyone? It is easier to take off the first hydrogen. Yeah, when you take off the first hydrogen, you now have something that's negatively charged, right? And you're trying to rip off something that is positive, right? As another hydrogen, so it's going to be held tighter. and it's going to be harder to do. We actually see that for every hydrogen that comes off, there's a Ka value. So this is Ka1, which represents the first hydrogen that comes off. This is the Ka2 value for the second hydrogen that comes off, and the Ka3 value. If we look at something like phosphoric acid, which has 3 hydrogens, the first Ka value is to the -3, second one's like to the -8, third one is to the -13. The Ka values get smaller every time a hydrogen comes off. As the Ka values get smaller with each hydrogen that comes off, a smaller K value means we have more reactants, which means less H plus is coming off. So it gets harder and harder to remove an H plus as you go through it. So when we want to do a problem that involves a polyprotic acid and we want to do a calculation to figure out the pH, the concentrations of everybody, we do have to do several things. And so we'll take a look at an example here of one. We'll come back to this in just a second here. All right, so let's say we wanted to figure out pretty much everything. We wanted to figure out the concentration of everybody in phosphoric acid as it breaks apart and loses one hydrogen after another. And we also want to figure out the pH. So we have a 5 molar solution of phosphoric acid, which is H3PO4. And once again, what's going to happen here is the very first hydrogen will come off, and we'll be left with H2PO4 minus. And that is our Ka1 sort of reaction. The next thing that will happen is our H2PO4 minus will lose an H plus and an HPO4 2 minus. That would be our Ka2 reaction that happens. Lastly here, this guy will lose that final hydrogen. And we'll form some phosphate here. And that would be our Ka3. So in this particular problem, we want to know pretty much the concentration of everybody along the way when we do this. So let us take a look at this and how to approach these problems here. So we're going to start with a 5 molar solution of H3PO4. So the very first thing that's going to happen when we do this is we will get the phosphoric acid to break apart into our H plus and our H2PO4 minus, as we just saw. That's going to be our Ka1 value of 7.5 times 10 to the -3. We're starting with a 5 molar solution. So our ice table is going to be kind of like normal. It's going to be 0 and 0. Our change will be minus x plus x plus x, which means at equilibrium here, we have 5 minus x, we have x and x. Any questions on the ice table here? So very similar to what we did before. We're going to put this into our Ka1 expression. So our Ka1 expression here is going to be like any other one, our products over our reactants. And once again, this will equal our 7.5 times 10 to the -3. We're going to put our numbers in. That will give us x squared divided by 5 minus x equals 7.5 times 10 to the -3. Get that 3 to right there. I'm going to assume that x is equal to 0. Kind of hope for the best here. We're going to assume that x is equal to 0. And if we do that, that will give us x squared divided by 5 is equal to 7.5 times 10 to the -3. Once again, I'm going to multiply to the other side and take the square root. And if I do that, we'll take 5 times 7.5 to the -3 and a little square root action. Going to give us an X value of 0.194, we'll call it. We do want to check it, so we'll take 0.194 divided by 5 times it by 100%. And we will see that we are good, which is why I changed the concentration years ago. So we are good here, this check. So this check is okay. So after the first dissociation here, when the first hydrogen comes off, we actually have some answers to our question. We see that the H plus concentration here equals X. So that means that the H plus concentration, which equals X, would be 0.194 molar. We also see that the H2PO4 minus concentration equals X. So we do have from this first table the H2PO4 minus, and that also equals X, which is 0.194 molar. And we have the phosphoric acid concentration at this point, which would be 5 minus 0.194, and that would get us 5 minus 0.194. We'll call it 4.81 molar at this point. So from our very first ice table, our very first hydrogen that came off, we were able to really knock out a few of these things. We were able to knock out this guy, we're able to knock out this guy, and we're able to knock out that guy's concentration. Any questions so far? We still are interested in this one, which we find happens right here in the second step. So that is going to require us to do the second part of the dissociation. So that is where we're going to pick up here. So the next thing that's going to happen is that guy is then going to lose its second hydrogen off of there. And this would be our Ka2 value of 6.2 to the minus 8. So initially here, do I have any of this concentration to start with here at this point? I actually do. It is the equilibrium concentration that we got from the first table. So that actually would be 0.194. Do I have any H plus from the first round? I also do. Again, it is the equilibrium concentration here from the first step, which would also be 0.194. And I do not have any of that guy. So we do have some initial concentrations, which are our equilibrium concentrations from the previous table. The change here would be minus X plus X plus X, which means at equilibrium, we would end up with 0.194 minus X, 0.194. This is actually plus X, and this is X. Any questions on that table? So our equilibrium concentrations from the first step become our initial concentrations here as it continues to dissociate. We're going to put it into our Ka2 expression, which is our H plus, our HPO4 2 minus, H2PO4 minus, and again, that's going to equal our 6.2 times 10 to the minus 8. Putting in our values here, we will get up on top 0.194 plus X times X divided by 0.194 minus X, and that would equal 6.2 times 10 to the minus 8. We're going to assume X is equal to 0 because why not? It worked on the first step, so why not? That is going to get rid of this X and this X. And that will give us 0.194 times X divided by 0.194 is equal to 6.2 times 10 to the minus 8. I think I could do the math here. That's going to cancel. And that gives us an X value of 6.2 times 10 to the minus 8. We do want to check it. So we'll take 6.2 to the minus 8 divided by 0.194. Times it by 100, and you're nowhere even near 0.1%. So the check here is good. That means that now from this table, we have now gained another piece of information from the second dissociation, the concentration of HPO4 2 minus equals X, which equals 6.2 times 10 to the minus 8 molar. What happens when I take the X value and put it into here? What do I get for the H plus concentration? You take 0.194 plus 6.2 times 10 to the minus 8, you still get 0.194. It's super small, yeah? You take 0.194 minus 6.2 times 10 to the minus 8, you still get 0.194. So since it's a really small number, not much has come off here, as we could see in this case. So from the second dissociation step, we were able to pick up one more piece of information we were looking for, which was this guy. That leaves us really phosphate, which the only place where phosphate's at is in the third step. So we're going to then do the third dissociation step here. And at that point, what's going to happen is H2PO4. I feel like I have an extra H in there. I do. That again. HPO4 2 minus will lose one more H plus. And that will make our phosphate, which is what we're looking for as well. This would be our Ka3 value, which is 4.8 to the minus 13. Once again here, we're going to get our initial concentrations from the previous table. So our initial concentration here of the HPO4 2 minus is 6.2 times 10 to the minus 8. As we saw from the previous table, when we do put our number back into there, we do end up with 0.194. And this is going to be 0. Change here would be minus X plus X plus X, which means at equilibrium 6.2 times 10 to the minus 8 minus X, 0.194 plus X and X. This will go into our Ka3 expression, which is the H plus, the PO4 3 minus, and our HPO4 2 minus will equal our 4.8 times 10 to the minus 13. Put in our numbers, 0.194 plus X times X divided by 6.2 times 10 to the minus 8 minus X equals 4.8 times 10 to the minus 13. No sense not assuming X at this point is equal to 0. When we do that, that will get us 0.194 times X divided by 6.2 times 10 to the minus 8 equals our Ka value there. I ran out of room, so I'll just put my Ka3 there. We're going to multiply this to the other side and divide it. So when you do that, taking the Ka value, which is 4.8 to the minus 13, times it by 6.2 to the minus 8, then dividing by 0.194 will give us an X value in this case of 1.5 times 10 to the minus 19. Again, we do want to check it, so we could divide it by 0.194 and times it by 100, and not much is happening there. It's really, really small, so the check is good in this case. That means from our table, we could see that the concentration of phosphate equals 1.5 times 10 to the minus 19 molar. Once again, if we put our X value into this spot right here and this spot right here, these numbers will not change because it's super small value at that point. Any question on that there? So in this case, we had to go through all three of the dissociation steps because we were interested really in phosphate concentration at the end. But let's talk mainly about what is really happening here as we go from the first H coming off to the second H coming off to the third H coming off. Where did the majority of the H plus come off? Which step? The very first step. Our very first step, we had a concentration of 0.194 for the H plus. When we got to the second H that came off, all that we got to come off was a measly 6.2 times 10 to the minus 8, which was a really small amount that came off. And then when we got to the really next step, even less sort of came off there in terms of how much really kind of dissociated. So when you're dealing with a polyprotic acid and you're interested in really only calculating like the pH of what it would be, it is usually in most cases pretty safe to do it based off of the first H plus that comes off. So the amount of the first H plus that comes off would allow you to calculate the pH of that solution, which we do need to do here. So the pH would be minus the log of 0.194, which is our H plus concentration pretty much all the way through. That would give us a pH in this case of 0.71, which is definitely acidic in this case. Yeah. So in a case of a polyprotic acid, you can just do the first ice table with the Ka1. You could use the H plus concentration and calculate the pH, and you probably will be pretty good in almost every case. If it is a question like what we had here, where it wants really the concentration of everybody along the way, it may require you to do the second sort of dissociation, or in this case, like the third dissociation that would come off. Any questions on polyprotic acids? All right, and that's pretty much what that table there that we skipped says. Basically, the first dissociation step is most important in terms of the pH. As it gets progressively harder to take off the H plus concentration or the H plus as you go from one step to the next. That wraps up this chapter. Any questions?